Hello and welcome back. I am Andrei and today we are going to review the paper Concept Bottleneck Models. This is a recent paper and was published at ICML 2020. Now the authors are Pang Koch, Tao Nguyen, Yeo Tang, Stefan Musman, Emma Pearson, Bean Kim and Percy Liang. They are affiliated with Stanford and Google. Now, this paper is about learning interpretable models that allow users to interact at test time with concepts in order to improve the prediction. So the topic of this paper is deep learning interpretability with a focus on concept-based explanations. But now let's closely review the abstract, then walk through the paper, review the method and the experiments, and get the insights. So they seek to learn models that they can interact with high-level concepts. So they seek to learn interpretable models, but with concepts. Now, they are saying the state-of-the-art models do not typically support manipulations of concepts such as the existence of bone spurs, and they are trained end-to-end to directly predict from raw inputs. So this is going to be the central idea of the paper. They want to make models that predict firstly concepts, and then they predict the actual label, the actual prediction. And let's look at this figure. And we see here that we have the input, and essentially the model is composed of two parts. We have like a normal CNN, but instead of predicting the actual prediction, we have an intermediate, call it representation, which is based on concepts. So these concepts want to be humanly understandable concepts such as sclerosis, bone spurs, and then based on this, call it intermediate representation, we use another model, in this case a regressor, but in the next case it's going to be a classifier, doesn't matter, in order to make the actual prediction. So we are going to see that we define the first part as the function g, we define the second part as the function f, and then the whole model is going to be f of g of x, right? So we get the input, we get then with g the intermediate representation, and then through f, meaning this last bit, we get the actual classification, the actual prediction. Now, the whole point of this paper is that revolves around this intermediate representation, and they want to essentially investigate whether having a intermediate representation based on concepts, right? So these are not just random things, it's just every single one of these let's say outputs represent a concept, whether if let's say a doctor has the prediction at test time, and if they come and see that, hey, the model didn't predict well a specific concept, they want to test whether if the doctor fixes this, so if doctor puts the correct input for specific concepts, like let's say this last one, how much does that improve the prediction and how it actually works at test time. So the core of the paper is to investigate this idea of concepts bottleneck. This is why it's even called concept bottleneck, because it has this, call it bottleneck, but they focus on test time intervention, and we are going to see that. Now, they admit that they revisit the classic idea of first predicting concepts that are provided at training time. This is going to be important because these concepts, they need, like, you are going to need another annotation. This is clearly a drawback in some cases because it just requires more time, more money to get the annotation, so that's the problem. But we are going to see that it slightly improves the prediction accuracy when you have these concepts. So for example, if it's going to be harder for you to get more data, like actual training data, like actual new inputs, you can pay somebody to just grab more concepts, meaning get more information from your data. It can be a use case, but I think that in most cases it's going to be a drawback to have these annotations, but my opinion. Now, they want to let's continue. So by construction, we can intervene on these concept bottleneck models, exactly what we discussed that they want to intervene, by editing their predicted concepts values and propagating these changes to the final prediction. So they want to change that at test time and see how it works. And the core results are that they test it on 2 data sets. So they have a medical data set, let's say data set 1, and they have a birds classification data set. And they are going to get competitive accuracy, meaning similar accuracy, then standard end-to-end models, while we enable this interpretation in terms of high-level concepts, right? Okay. Now, the main contribution of the paper, it's outlined right here, and they systematically study variants of concept bottleneck models. So this model right here that we saw, we are going to quickly see that it allows multiple ways of training. It's like, do you first train the first bit, then the second bit, do you train them end to end, and so on. There are multiple ways of training that, and they systematically study these variants. I have to say that this paper is more, let's say, an ablation study kind of paper. It tries to actually understand what happens with the concept bottleneck models. This idea of an intermediate representation is not new, but they thoroughly study it, and I think the paper answers most of the questions that one could have. And they contrast it with standard end-to-end models in different settings. Yes, we have 2 data sets. Okay, so the questions that they are trying to ask, like, is there a trade-off between task accuracy and concept interpretability, and so on. But the point is they take this idea of concepts and they do a thorough analysis on that. Now, from the related work, something which is going to quickly come into mind while we present the method is that they mention that it's relatively common to have an auxiliary loss. So the way, let's say, this auxiliary losses, call it a multitask learning, is that you have your input and you have, let's say, your model, and you try to get your prediction. But this end-to-end training might not be well, like it might overfit, it might do something else. Now, from your input X, you can get not only one label, you can get, for example, 2 labels, right? You are interested in just label 1, but you can get an additional label from the actual paper, from the actual input. And now you, in your loss, you are going with your model to try to predict 2 of these things, with the idea that, hey, if you make like 2 predictions, you essentially have more information into the actual data because you have 2 labels rather than 1. You are interested in only 1, but you use this label 2 as auxiliary, meaning to get more information from the data. Your loss is composed of both, and you essentially try to get a better model, but by learning it to predict 2 things. So the loss is going to be, let's say, a loss on y1 plus a loss on y2. This is the auxiliary loss. This is what they compare with because it's something relatively common in the literature. Now let's move to the actual method and see how it actually goes. So here we have the setup, meaning the model. Now, okay, we observe that the training points, we have n training points. I want to remind that in the training data, we need the annotations for the concepts. So the concepts are a k vector of k components. We discussed that we have, the model is split into two parts. So you have your input. Now, your input passes through, let's say, a CNN, which extracts some concepts. This is the concept. And then you get these concepts and you further predict your actual thing that you want, your actual label. So this is concept bottleneck model. Now in the standard case, you just go from an X to a Y. So this model adds this thing. Okay, now we are going to present a few things, but I want to make sure that it's clear that here they are doing, so this analysis is made on regression first. It's going to be the same in classification, but I want to make sure that you got that. Okay, this is our classical prediction. Nothing interesting here rather than two things. So our loss is going to be composed of two things. We will have a loss on the concepts and a loss on the actual prediction. So the loss on the concepts, it's essentially going to be attributed with here, right? So this is loss of the concepts, and in here we are going to have a loss based in the actual prediction. And this goes back to multitask learning. So this was multitask, because we essentially want to predict well both the concept and the actual label, the actual prediction. In multitask you needed only one, but you are predicting two. Here in this case it's an analogy, like we want both to be predicted well. This was the analogy that they wanted to make. Okay, now the interesting bit is that, you see, the model is like, let's say, sequential in a sense, meaning it goes only one way. There are two models, meaning F and G, but they are put in a sense end to end, like the output of G gets the input of F. And now they systematically learn, hey, how should we actually train this? Like, should we train G and F separately, meaning independently? Like, you train G on the true X and true C, you train F on the true C, true Y. This is one way. But there are multiple ways. Like, you could, for example, train them sequentially. Like, firstly train G as the first thing, and then train F not on the true data, but on the prediction of C. Let's see more concretely. So, we consider the following ways to learn the model. Model is composed of these two smaller models. We have independent bottlenecks. So we learn the two models independently. We firstly essentially optimize the first model, and then we optimize the second model. What needs to be clearly noticed is that we train F on the true labels. So everything is trained on the true labels. Now, there is also the sequential bottleneck way of training things, where we firstly learn G in the same way as above. So G is learned, I mean, it's just normal learning. But then when we learn F, instead of the actual training data, we train it on the G's prediction. So notice this here is the G prediction, while in the independent case there was the actual data. Now, we have this joint bottleneck where we essentially train them at the same time, right? So we train both models. You see that you take argmin of both, so it's both sides, where this is essentially the loss for F, and this is the loss for C. Notice that in this case we also train on the prediction, and there is this parameter lambda in here, which is just a hyperparameter that controls the trade-off between the concept and the task loss. So this thing is called the task loss. Your task is to actually predict Y, so this is the task loss, and this is called the concept loss, because you predict the concepts. And the last thing is the standard model. This is nothing more than just classical end-to-end training, because we ignore these concepts. Now I want to make something clear, and that is, to actually get a concept bottleneck model, you pretty much do not need to change anything to your model. Like if you have a neural network, it's composed by multiple layers, and this is your actual prediction. Let's say that you put X, then remember that C is part of RK, so it has just K inputs. You can literally do nothing else than get your standard, ResNet, and this is what they do. So consider that this is a ResNet. They use a ResNet 18 backbone, and then this is the last CNN, and then you do nothing more than just put, for example, K. You can put a linear layer with K outputs in here, and this are going to be your concepts, right? There are K, these are your concepts. So this can be, for example, your G. You get from the input to the concepts, and then what they do is that to get your actual prediction, because this is what you're interested in, you can put, for example, an MLP with 3 layers. This is what they do. So they get the normal ResNet, essentially, to predict the concepts, and then they put this MLP, multiple layer perceptron at the end with 3 layers, and you can train this thing end to end, because you can just apply back propagation on them, and you have 2 losses. You have your task loss and you have your concept loss. So it's nothing special in training this. Now let's go and actually think about what this thing actually matters. Let's analyze this method. As a pro, you can apply it to any model. This is a good thing. You make a minimal change of just changing, for example, the last layer. Okay, now the problem with this method is that obviously it requires annotation, and if we use this joint training, which is presented here, we obviously need to do some hyperparameter tuning on the lambda. This is typically a problem. But let's move on to the experiments and see what they do. So they have 2 data sets. We talked about them, one with X-ray and one with bird identification. Not many interesting in here that outside of the fact that, so in bird identification, the concepts, they took 112 binary concepts. Now it's not actually 112, so they took them using Amazon Mechanical Turk. So from these 112 concepts, they have something like, is color red, is the bird blue, is the bird let's say yellow. So it's not like 112 concepts. It's like one concept is essentially one hot encoded. This is one thing, and I think this is what matters. Now let's look at the results. So they model this X-ray as a regression task, and the bird identification is a classification task. Now here we look on the task error OIE. This is the X-ray. You see that the performance is not like accuracy something because it's a regression, so it's root mean squared error. Now notice this is the independent training, this is the sequential, this is the joint. We have the standard model, so it's a ResNet with 3 layers. The no bottleneck is just a ResNet with a 1 layer at the end, nothing much. This is the multitask learning. They tried something like that. Notice few things. Notice there's this joint gets essentially, call it the best performance on the X-ray, and it also gets, let's say, the best performance on the birds. Surely it's a little worse than standard end-to-end in classification, but it's close to that and clearly better than independent sequential. So the point is, this joint seems to get the best results, but I'm not surprised in a way, because you train it, like if you look at this thing, you essentially minimize, both models at the same time. Like it's essentially end-to-end training. So it's not that surprising, but it's encouraging to know that it's happening as well. Okay, now let's look again here, and we see that, so this was the task error. Now this is the concept error, like how well does it predict the concepts. And notice again that this joint model, it gets essentially in the classification task around, like, I like to think that this error is the misprediction. So they get 3% misprediction, while the standard model gets 9% misprediction. So much better at predicting the concepts, but I want to take it a bit with a grain of salt. Like it was trained to train it with, so it was trained to predict the concepts well. So that's, it's nice to see that it gets, like 97% accuracy on predicting the concepts. This is good. Well, the comparison with the standard model, they mention it's much better, but the standard model does not get any concept annotation. It just doesn't. This idea of probe, it actually means that you have your model, you get the last layer, and then you train, for example, a linear classifier in here with the concepts to predict the concepts. So the model was trained end to end, no concepts, and then you extract, let's say, the features, and you train another small networks to predict the classification. So it's a bit misleading, but the point is, it is very well that we get very small error for the concepts, because when you want to change a concept, like going on the first page, if you want to leave the radiologist to check whether one of 100 concepts was well understood by the model, it's good that they know that it's gonna be, let's say, 1, 2, 3, 4 concepts which are wrong, but not 50%, because if 50% of the concepts are predicted badly, then there is no point in you changing one. Ideally, you want, from 198 to be corrected, to be correctly predicted, and then the radiologist comes and fixes the last 2 and gets the final model. But this is encouraging for the thing that the models predict well. That. Now let's go to the actual another thing. We discussed about that hyperparameter that the joint needs to solve, and we need to look into here. So this is the X-ray, and on this line we have the bird. Now I want to make sure that it's clear what are the axes. So here we have the error, and here this is the concept error, and here we have the task error. Now, ideally you want it to be as close as possible with that thing. Look at the errors. Here clearly lambda 1 is correct. The other ones are very close by, to be frank to you. But if you look into this one is close, this one is close, this one is close. Now, this one that I firstly, it's quite bad. Like, if you look on the axis, it's like 0.15, while these are 0.2, no, 0.02, so it's like 7 times more. So I would say that all these are almost the same, my opinion. It's not a big difference on the y-axis. So I would go looking at this data, I would say that a safe bet is lambda equal with 1. Don't take my word as it is, but I mean, from this data, it seems to me that lambda is equal to 1. And let's actually understand what this lambda equals 1 actually means. So it means that when you train the joint bottleneck model, let's look a bit here. So when you train this, let's be clean. When you train the joint bottleneck model, this lambda is essentially saying, hey, so how much do you want to penalize when the task is bad and when the concepts are bad? And lambda equals 1 means, hey, to the model, both the task and the concept should be equally important. Like, there is not much difference. Like, put the same importance on both losses. Sure, the losses can be on different scales, but put the same importance for the losses. This is what this is saying. Now, yes, you can take a 0.1, so that means that the task is 10 times more important than the concepts. But let's say, between 0.1 and 1 seems to be the safe area. Now, let's look further and some more results. And this is call it meat, the actual thing that they want to say. So they say this, they call it test time intervention. And this image tells it well. So you start with your actual input, and your model makes a prediction on the concepts. Now, in this case, a doctor can look, hey, this concept is badly predicted, fix it. And then when you fix it, the model essentially predicts well. When you didn't fix it, the model predicts it wrong. Yes, I get this. It seems to be, it sounds at first to be a practical use case. But the question which is going to my mind is, hey, assuming that you have, like 100 concepts, how is the doctor going to check? Like, is he going to check all these 100 concepts? Like, I don't understand how would it be in practice, because if you have many concepts, it's just gonna take much time to check all of them. And this also assumes that they know exactly what's the right answer to the concept. It's not very clear to me how this would work in practice, but something more interesting which it allows, and I think this is more interesting, is that it allows counterfactual explanations. So, for example, having a specific concept vector, you can change specific things in the concept vector and see what happens in that case. Like, hey, let's say in this case, if the gap between two bones was higher, what would it happen? Does the model lead to a bad prediction or a wrong prediction? Or if there was another, let's say, concept such as, is the bone fractured? Like, what will happen to the model if it's fractured or not as a concept? So you get counterfactual explanations. But you could get this thing just because you have the concepts and then you have this F which gets them. So doesn't this idea of getting counterfactual explanation is not unique to the paper, but it's still good to know. So this is the idea of intervention, test time intervention. Now let's see what's the actual result when you do that. So we have test time intervention results, and these are the things. I want you to focus firstly on the first and the third one, and then we are going to look in the middle one. So here, the one that got the best results previously was this joint. And notice that as you intervene in more and more concepts, so you get this joint, you get improved performance. Now, on this task, there are just 10 concepts in general, so I would assume that somebody would fix, let's say, 2 concepts, and you get like a 25% decrease in the loss. It's not bad. It confirms the idea that if you change, meaning fix, the mispredictions in the concepts, then it improves. So it's good to confirm that it improves. Now here in the birds case, so the number of concept groups intervened. Now they take this idea of groups. I told you that they have, for example, if it's red, if it's blue, if it's dark, they one in hot encoded everything. So this thing is, let's say, a color group. So you fix a color group essentially. Now you see that again it confirms that the error decreases. This is good, but if somebody does this, they are not going to fix 10 groups, because or maybe, but it seems weird to me that somebody would fix 10 groups, because if you fix 10 groups, you essentially fixed 3 per group, like 30 things. Then it seems complicated, but it's good to see that it increases the performance. I'm not sure how people would do this in practice. And the other things which needs to be seen from this graph, let's clean, is between the first and the second images. So it's the same data set. The single difference in this idea of non-linear and linear. So I told you that they use a ResNet, and then they have 2 things. They either use an MLP with 3 layers, calling this the non-linear things, but they also use just 1 layer. So essentially F is either a 3-layer or a 1-layer network. 1 layer is the linear. What needs to be noticed is as follows. The performance initially, like no concept intervenes, is essentially the same. So it's the same. F works even with 1 layer in this case. But as more concepts are intervened, then here the performance essentially does not improve, or it jumps for the joint. Basically, call it this way: when you have a very simple F model from the concept to Y, the performance essentially doesn't improve much, while here a bigger model takes much more advantage of this increased capacity in the model. They argue that this gap, because you start from the same point but then you get with this gap, they argue that it might be in the way like how this model F deals with distribution change. And I agree that yes, because it's a distribution change. Like when you train it jointly, it's not trained on true concepts. It's trained on G predicted concepts. And here, when you test time, you essentially get it to the true label. So it is a distributional shift, but I would much rather say that this larger model, like the 3-layer MLP, it just has more capacity, so it can do much more with the additional signal. I think this remains for further investigation, but the point is that the improvement at test time intervention is very dependent on how well the chosen architecture works with distribution shifts. Like your potential improvement at test time is highly dependent on F. Like this is a thing to keep in mind. And I think they have a bit more experiments, but we get to the actual conclusion, and that is that this concept bottleneck models, they achieve comparable performance to standard models while they allow test time intervention. this idea of reaching similar performance, in a way, what's negative about that is that it requires more training annotations. It just does. So in a way, you have additional training signal because you have more. You have essentially an additional loss with additional training data. But on the flip side, these concepts might not be complete. Like, you put some concepts, but they are not going to fully cover all the concept space. So you have more, call it input signal, because you have different annotations, but you do not have all the concepts. I mean, surely you can't. I bet you can find another concept which wasn't put here. Or for example, in the case of this X-ray, they have only 8 or 10 concepts, so clearly that's not enough to fully define it, but still the model reaches same performance. So as a conclusion, these constant bottleneck models, they achieve similar performance to standard end-to-end models with requiring annotations, but possibly having incomplete concepts. Again, it's not clear to me how one could use this in practice at test time, because I don't see how somebody can fix like 10 concepts. And the improvement, but still the improvement at test time intervention exists as seen from these graphs, but is a bit dependent on how well the chosen architecture works. Now overall, this is an interesting paper because it does a more in-depth, good ablation test over this idea of concept bottlenecks. I think it answers some questions. It answers some good questions, like for example, can you not put all the concepts? Yes, you get similar accuracy. So it's a good analysis, and it raises new questions. So good paper. And yeah, I was Andre. If you enjoyed this video, I'm going to make more, so definitely subscribe to this channel, and thank you so much for watching. See you in the next one.